The next example we'll look at is example 4. This is yet another example of a separable ODE. We want to get all of the x terms on one side and all of the y terms on the other side. Easiest way to do that for this one is we can, first of all, multiply both sides by dx. Clear off that fraction. We have e to the 2y minus y times the cosine of x dy is equal to e to the y sine of 2x dx. To get rid of this cosine of x term that's on the left-hand side, that's with the y's, I can divide both sides by cosine of x. And similarly, to get rid of this e to the y term, this hanging out with the x's, let's simultaneously divide both sides by e to the y. When we do that, we should get the following cancellation. Here, the cosine of x's cancel, and so we're left with e to the 2y minus y divided by e to the y dy. That's what we wanted. We have a function of y times dy. And over here on the right hand side, we see that the e to the y cancels, and we're left with the sine of 2x over the cosine of x times dx. So we were able to go ahead and separate our ODE, and now the next step would be to go ahead and integrate both sides. For the left hand side, let's split it apart. Let's rewrite this thing. We can write this as e to the 2y divided by e to the y minus y over e to the y dy. This is equal to, on the right hand side, we can use a trig identity. In particular, the sine of 2x is 2 times the sine of x times the cosine of x all over the cosine of x. And now that cosine term is going to cancel. So we have the, let's see if I can make some room here, the integral of this term here. When you divide by like bases, you subtract the exponents. That's simply going to be e to the y minus, let's rewrite this as y times e to the negative y dy. And this is simply equal to 2 times the antiderivative of sine of x dx. I'm going to go ahead and get some more room over here. And as always, let's start with the easy part first. Let's integrate the right-hand side here. The antiderivative of the sine of x would be negative cosine of x. So this is negative 2 cosine of x. And we'll put our constant of integration over there. So we'll do our plus c. Now let's focus on this thing here. The antiderivative of e to the y, we know that that's going to be e to the y minus, and now we need to do this part here. So I've already incorporated the minus sign when I wrote it over here. We need the antiderivative of y e to the negative y dy. This is a good old blast from the past, some good review of Calc 2, but in order to do this one, we need to use integration by parts. In integration by parts, you let u be the polynomial part, so we're going to let u be equal to y, in which case our du will be 1 dy, and then the dv is going to be equal to the exponential part, e to the negative y dy. You would integrate that to get v using a u sub. We would get negative e to the negative y dy. And then via integration by parts, this should be equal to, it's the u times v. So we're going to get u times v, which gives us negative y e to the negative y minus the integral of v du. v is this, du is this, so it's negative e to the negative y dy. This negative and this negative would make a positive, and then when you integrate this with u substitution, we'll pick up yet another negative sign from the u sub, so that's going to be minus e to the negative y. So just plugging that in, we have the negative of y e to the negative y minus e to the negative y. We can go ahead and distribute our sign in, so we get e to the y plus y e to the negative y plus e to the negative y is equal to negative 2 cosine of x plus c. So this would be our general solution. This one was an initial value problem. We want to solve for the particular solution when y of 0 is equal to 0. So let's actually go ahead and do that. So everywhere we see an x, let's put 0. And we see that the value for y itself is going to be 0. So 0 for x, where'd it go? 0 for x, 0 for y, so we're going to get e to the 0 plus 0 e to the negative 0 plus e to the negative 0 is equal to negative 2 times the cosine of 0 plus c. And this should allow us to solve for c. E to the 0 is 1. This is a coefficient of 0 times 1. That's going to be 0. Again, e to the 0 is 1. The cosine of 0 is 1 plus c. So we get 2 equals negative 2 plus c. Add 2 to both sides, and we should get the c is going to be equal to 4. So if we go ahead and plug it in, the solution to the initial value problem, which is the real answer, not just the general solution, is as follows. It's e to the y plus y e to the negative y plus e to the negative y equals negative 2 cosine of x plus 4. So this function satisfies that original differential equation which I erased, and it satisfies this initial condition.